Good morning. Cooling represents a critical challenge for 3D heterogeneous integration for several reasons. One, the power density and the total power of a 3D stack can be very large. Two, thermal crosstalk between adjacent tiers can be significant. And three, conventional cooling is typically only limited to the top layer of a 3D stack. To illustrate these points, please consider the 5-chip stack shown here of high-powered chips. Assuming conventional air cooling from the top layer results in junction temperature in the 3D stack that are completely unacceptable, using liquid cooling from the top of the 3D stack still results in junction temperatures that are unacceptable. And even if one were to develop a liquid cooling solution from the top of the stack to enable lower junction temperatures, there are many 3D heterogeneous microsystems require unobstructed view from the very top surface of the stack in order to enable optical millimeter wave communication and sensing. Thermal crosstalk is another challenge, and it's shown here, and it manifests itself as having the thermal map of a high-power chip being directly coupled and mirrored into a neighboring low-power die. This is a challenge because some of these low-power die can be photonic and memory in function, which are temperature sensitive and would benefit from thermal shielding. So to address the cooling needs, mitigate thermal crosstalk, and free up the top surface of a 3D stack to enable millimeter wave communication, here we explore the use of interlayer microfluidic cooling within a 3D chip stack. To implement this, not only would you need a fluidic channel within a 3D chip to dissipate the heat, but you must also develop through silicon via technologies that allow you to create signaling and power delivery between the tiers. One implementation of this is shown here, in which we have an array of micropin-fin heat sinks distributed across the chip, and where basically as the fluid flows across these cylindrical structures, which are made out of silicon, heat is rejected. Simultaneously, through silicon vias are created within the microfluidic heatsink, and that's represented by the orange-colored lines and dots. SEM images of such microfluidic heatsinks that have a combination of electrical and fluidic and electrical functionality are shown in the bottom right corner. And of course, for this to be successful, not only do you have to design the microfluidic heatsink to meet the thermal resistance and the pumping wear requirements, for example, in a 3D chipset, but you must also meet the electrical requirements of the interconnects that have to go through this microfluidic heatsink. For example, the density of the interconnects and the parasitics of the interconnects. Manufacturability, integration, and reliability, of course, are key. We have successfully integrated such cooling technologies in active silicon. Here we show an Intel i7 processor that have been post-processed with the monolithic microfluidic cooled heatsink, and measurements demonstrate approximately 40% lower thermal resistance compared to a copper plate solution. Further, we have integrated this microfluidic cooling technology, again monolithically, on an Intel Stratix 10 FPGA, which consists of 4 transceiver die and a central FPGA, all interconnected using EMIB. Measurements demonstrated 10x reduction in thermal crosstalk between the high power density transceivers and allowed us also to dissipate almost 50% more power within the package for the same junction temperature as a conventional or air-cooled version of this. All fabrication that was performed on these chiplets and post-processing were done at Georgia Tech cleanroom facilities, which support advanced 3D HI prototyping. So, given the promise of this technology, question is, how can we potentially bring this to life and implement it in a 3D system? Well, today there's a growing ecosystem for building chiplets of various functions, for example, digital, millimeter wave, analog, I/O, power, and so on. We believe that also chiplets can be used to build important package functions. So here we illustrate the idea of building an array of chiplets that are cooling chiplets. And these cooling chiplets are designed to meet thermal performance needs of a 3D system. So based on the thermal requirements, one can design the micropin fin height, diameter, pitch to meet thermal requirements. Simultaneously, these cooling chiplets would offer an array of interconnect options through them. In the bottom two left figures, we show TSVs integrated within this cooling layer that are probably more amenable to a digital system. On the right side, we show coaxial through silicon vias formed within a microfluidic heatsink to enable millimeter wave connectivity in a 3D stack. And so, given with all the advances that have been happening in 3D HI recently, we believe that we can basically hybrid bond. For example, these cooling chiplets in a 3D stack with active chiplets. And so that way you can bring liquid cooling directly to where you need it in a 3D stack without obstructing the electrical connectivity needs in the stack. Beyond cooling, at Georgia Tech, we're developing other chiplet technologies to provide other important package functions, including in photonic and millimeter wave. We have developed at Georgia Tech chiplets that mechanically self-align to each other in order to enable very efficient optical fiber attachment and alignment. Recent work demonstrates that chiplets can self-align with each other within 250 nanometers. And more recently, we've demonstrated millimeter wave chiplets where the sole function is to provide low-loss, seamless connectivity across an array of millimeter wave chiplets, irrespective of their heights, pad density, and pad materials. And with this, I really want to thank you for being here and giving me this opportunity.